By 2015, more than 10% of the world's hydrocarbon production will come from deep offshore reservoirs. To overcome the challenges inherent to conditions of increasing complexity, Total, world leader in deep water development, continues innovating to gain new ground beyond the current limits of the deep offshore. Total's track record in this technological adventure is an impressive series of successful, groundbreaking projects. Girasol was the first major development under 1,400 meters of water. One of the key innovations here was the riser towers. Dahlia holds the record for the largest number of ultra-deep subsea wells. Rosa stands out for having the longest tieback to a floating production storage and offloading unit, FPSO. Pazfloor boasts the world's first application of a seafloor gas-liquid separation system on such a large-scale deep offshore project. Moho Bilondo is Congo's first deep offshore development. Akpo is Total's first deep offshore development in Nigeria. And so Total has been pioneering deep offshore through a series of cutting-edge technological innovations. Ensuring fluid flow from the reservoir to the floating production unit and preventing hydrate formation and wax deposits, while achieving economical development, are some of the most critical challenges to be faced in the production of deep offshore oil fields. In a context where preserving the environment and securing a high level of safety for personnel and installations take pride of place, the flow assurance challenges involve complex operating procedures and demand more and more innovative technological solutions. So far, hydrate prevention relies on the installation of a production loop architecture composed of 2 production lines and complex umbilicals, and on preservation procedures. In the event of a production shutdown, this development scheme is designed to circulate an inert fluid to replace the oil produced, and uses hydrate inhibitors, like methanol, that must be handled with the utmost caution.
It is true to say that the progress we have made in the development of new technologies is really impressive. But strangely enough, the techniques that enabled us to develop and produce large fields today are not suited to the deep offshore targets of the future. Some of the main difficulties we have to tackle are those raised by smaller accumulations that lie far away from the existing production hubs or the shore, and are often located in harsh environments. Producing these resources of the future requires new technical solutions for subsea tiebacks with a step-out distance of up to several hundred kilometers, but also finding innovative ways to reduce investments and streamline field operations.
Having pushed the boundaries of thermal insulation technologies to the limits, Total's R&D teams are now working on new development schemes involving innovative technologies such as subsea processing, electrical heating of production lines, and composite materials.
We are currently studying the electrical properties of carbon fibre. The main aim of these experiments is to use the resistivity properties of carbon fibre in an electrical system and subsequently to install the device either in a subsea environment or onshore for preservation purposes. In this design, the carbon fibre will cover the entire tube and uniformly heat the oil flowing inside it.
Carbon fibre is an electrical conductor and has a number of advantages over copper used in electrical heat tracing. It is 5 times lighter and 10 times more resistant to tensile stress. Its electrical resistivity is 1,000 times higher than that of copper, making the heating process more efficient and distributing the heat itself more uniformly. With a self-heating carbon line, the temperature of the tube can be actively controlled, and the prevention of hydrate formation can be controlled optimally. The use of carbon fibre in new deep offshore development schemes is one of the key discoveries driving access to untapped reserves. Such state-of-the-art technologies and innovative development schemes bring a whole host of advantages in terms of simplifying production, enhancing robustness, reliability, economic viability, safety, and respect for the environment. Using heated single production lines and valves that are operated electrically rather than hydraulically opens up prospects for simplifying and lightening the umbilicals by eliminating the hydrate inhibitor and hydraulic fluid lines.
Carbon fibre has two characteristics that set it apart from electrical heat tracing. It is easy to install over long distances or on complex equipment like valve bodies, and if the outer surface is damaged in any way, the redundancy of the carbon fibre assures electrical continuity. As field operators, we expect carbon fibre technologies to offer solutions that are extremely reliable, offer extensive flexibility, and will perhaps, in the long term, provide us with an answer to the daunting challenge of eliminating chemical injection systems, which are highly problematic in terms of safety and environment, and makes things easier to operate.
Electrical heating can also be used to prevent fire protection networks from freezing in very cold environments like the Arctic, or to prevent corrosion under insulation. Yet another use can be spot heating of specific areas to prevent the top-of-line corrosion phenomenon in gas lines, for instance. What we foresee is a radically new concept of offshore development. The use of composites in heating systems will help us to streamline our operating procedures and get free of many of our current operational constraints. This will give us the key to new targets, either in the Arctic or on remote offshore fields that would remain unreachable using today's technologies.